Assalamu alaikum everyone. I am Satman Shahriar. Currently, I am working as a lecturer in the Department of Water Resource Engineering of. Recently, I have conducted my MSc from the Department of Water Resource Engineering. Today, I am going to present the findings from MSc thesis titled "A Study on Future Stream Prediction of Brahmaputra River Basin under Seismic Climate Change Scenarios Using Deep Learning Techniques." I have conducted my thesis under the supervision of Professor Basin. This is basically the outline of the presentation. First, let's look at the background. Accurate and reliable hydrological prediction is very crucial for effective water resource management, flood control, and agriculture planning. Consequently, streamflow prediction it has become the numerous focus of the numerous studies since the middle of the 19th century. Traditionally, two approaches have been used. One is conventional hydrological models. They are basically the physical process unit. And the other one is data-driven statistical models. They are basically the machine learning-based regression. Here at the bottom, you can see that two of the studies that have been conducted by Abdullah et al. And Alam et al. During 2024 and 2021 using the conventional physical process-based swap. They achieved accuracy up to 90% during the calibration period and up to 86% during the validation period. However, the conventional hydrological model they often struggle due to the multivariable data requirement, as well as the complex calibration constraints in order to accurately simulate natural processes. Therefore, deep learning techniques gain prominence for predicting stream flow because these techniques they do not require detailed knowledge about the underlying physical process. These are the previous studies that have been conducted on the Brahmaputra River stream flow prediction. At the top, you can see that Abdullah et al. Study they used physical process-based SWOT model in order to predict future stream flow of the Brahmaputra of the Brahmaputra Basin based on the recent CM6-based scenarios. The rest of the studies on this catchment, they predicted future stream flow of the Brahmaputra River Basin based on RCP-based scenarios. Therefore, in this study, we will employ deep learning-based techniques in order to predict future stream flow of the Brahmaputra River Basin based on the recent CM6-based SSP scenario. So, what are the study gaps in the research? Deep learning models, they remain underexplored for stream flow prediction in the Brahmaputra River Basin. Previous studies on other catchment, they primarily utilize observed precipitation, temperature, and as well as stream flow data as inputs for deep learning models development. But in this study, we'll employ only gridded precipitation and temperature data as deep learning models inputs, without the use of stream flow as model inputs. So that this approach aligns more closely with traditional hydrological models. In traditional hydrological models, we do not incorporate stream flow data as modeling. So the primary objectives of this study are to develop deep learning models, training and testing for simulating stream flow of the Brahmaputra River Basin at Bahadurabad outlet using observed climate data as modeling. To select the best performing deep learning model, and finally to simulate the future stream flow at the Bahadurabad outlet of 13 selected CM6 GCMs under the SSP 2 4.5 and SSP 5 8.5 scenarios using the best performing deep learning. This is basically the study area. So the Brahmaputra River Basin it expands approximately 580,000 square kilometers and it borders across China, India, Bangladesh, and Bhutan. The basin experiences extreme hydroclimatic variability with average annual rainfall which varies from about 1,200 to about 6,000 millimeters. The average yearly peak flow at Bahadurabad, which is situated close to the Bangladesh downstream end, is about 60,000 cubic, while the average annual flow rate is about 20,200 cubic, which makes it the fourth largest in the world. Another important reason why we chose this study area is because of the fact that Brahmaputra River Basin is one of the flood-prone catchments in the world. Let's look at the methodological flow diagram. So I have used WFE5 data source in order to collect historical climate data, which are basically the rainfall and temperature. But this is WFE5 is basically the bias corrected data set of the ERA5, which is basically a linear analysis data set. and it provides data at 0.5 degree by 0.5 degree resolution. But I had to downscale it at 0.25 by 0.25 degree resolution because the future climate data that will be provided by Mr. Arnese, they have a resolution of 0.25 by 0.25 degree resolution. So in order to maintain similar level of consistency, I had to downscale my historical climate data set as well. Then, provided damage inputs, I have developed my deep learning models to hyperparameter tuning. I have used 60% dataset as training and 40% as testing dataset and compared the outputs with BWD observations. I have selected 4 performance evaluation criteria. They are the NSC, R-square, P-bias, and RMC. And based on that, I have selected my best perfect deep learning model. And from CO613 GCMs, the rainfall and temperature at 0.25 by 0.25 degree resolution was provided as inputs to my best performing deep learning in order to simulate simultaneously the baseline flow, the near future, mid future, and the far future. The baseline period flow spans from about 1985 to 2014, the near future spans from 2026 to 2050, and the mid future spans from 2051 to 2075, and finally the far future it spans from 2076 to 2001. Once I have simulated my deep learning model for all of the 13 GCMs, I have done a multimodal ensemble of all these 13 GCMs in order to find the changes in the future annual stream flow as well as the changes in the future monthly maximum stream. Then using the annual maximum stream flow, I have done a flat frequency. This I have already described. These are the observed climate data sources from WFDE5. I had to do the bilinear interpolation technique in order to downscale them at a resolution of 0.25 degree by 0.25 degree. And these are the 13 GCMs that I have used for future climate data source. This is the architecture of the CNN LSTM model. This is the hybrid model. Here I have selected 2 layers of convolution operation and 3 layers of LSTM operation. The convolution block, they are primarily responsible to extract the spatial features, and the LSTM layers, they could extract the temporal feature from the tracks. Finally, all of them are passed to the fully connected layers in order to predict the next stream flow. This is the architecture of the LSTM. This is the architecture of the CNN model, and this is the architecture of the multi-layer perception model. Here, we do not provide any CNN blocks or LSTM blocks. All the inputs are provided directly to the fully connected layers. And all of the hyperparameters, they have been selected through random searching. These are some of the sensitive hyperparameters that need to be tuned. And I have used a mean square error loss function and Adam optimizer function. And I have selected a adaptive learning rate. And because the learning rate is very much influences the convergence. If it is too high, it may lead to instability, and if it is too low, it may slow the convergence rate. And I have used a callback function through a early stopping criteria, which ensures that our model does not overfit, because it will stop training once our testing loss it does not improve after several efforts. This is just a comparison of how the learning rate affects the model training. If you compare to the figure 7, figure 8, and figure 9, in the case of figure 9, the convergence is much more smoother, although the number of epochs is much higher. Because in the case of figure 9, the learning rate is much lower compared to the higher learning rate in the figure 7. Another important criteria which influences deep learning model is the number of the lag time, which will be used as modeling. So I have provided 8 trials from varying from 1 day lag length to up to 25 day of lag length. And here you can see that this is the hydrograph of the hydrograph during the testing phase of 2000 to 2040. In the case of 1 day lag length, here you can see the number of spikes in the hydrograph are much more. As we increase from number 3, this is the 5-day hydrograph, this is a 7-day hydrograph. During the testing phase, the spikes starts to decrease. This is the hydrograph during the 10-day. This is the 15-day. Here you can clearly see that the spikes almost vanished. This is also the continuation to 20-day lag length. This is the 25-day lag day length hydrograph during the testing phase. So as we increase the lag day, the number of the spikes reduce, which means that our deep learning model introduced non-linearity. Because the more there are variables, the more non-linear the equation becomes. So if I summarize the plot to figure 18, here you can see that the R-square value, it increases sharply after 15 days, which is indicated by the blue line, and it becomes flat almost after 15 days. In the case of RMSE through the orange plot or a line plot, here you can clearly see the dynamic value decreases sharply after 15 days, and it has almost become flat. So we have selected up to 15 days of lag length as our optimum day for inputs for deep learning. And this is a comparison how our input variables influences our deep learning model. If we have just used only rainfall, it would achieve accuracy up to 75%. And if we use temperature, it could provide accuracy up to 78%. Using both rainfall and temperature provided accuracy up to 86%. Because rainfall is directly contributed to the runoff process, while temperature is associated with indirectly the evaporation and the groundwater contribution. And this is a comparison of observed and predicted hydrograph for the hybrid CNN LSTM model and the other deep learning models. Here you can clearly see that our hybrid CNN LSTM model, which is a top plot, here you can clearly see that it could match both the extreme flow as well as the low flows compared to the other 3 deep learning. If we compare the accuracy to the performance evaluation criteria matrices, here you can clearly see that our CNN LSTM model outperformed the other 3 deep learning models, and it ranks as fast. In the case of training period, it could achieve accuracy up to 92%, and it could during the testing phase, which was about 86%, which is higher than the other 3 deep learning. So our best performing deep learning model was the hybrid CNN. So once we have selected our best performing deep learning model, we provided the inputs from the 13 series of GCMs from the Mishra dataset at 0.25 by 0.25 resolution to simulate the monthly maximum stream flow for the near future. Here you can see that the blue boxes are basically the baseline period flow during near future, baseline period flow, and this is the SP2 4.5 is indicated by the green boxes, and the orange boxes basically indicate the SP5 8.5 near future. This is the monthly maximum stream flow for the mid future. This is the monthly maximum stream flow for the far future for all of the 13 GCMs. If I summarize them through a multi-model ensemble, here you can clearly see that the left plot basically indicates the box plot during the multi-model ensemble of 13 models for the near future. Here you can clearly see that through a bar chart that all of the months show that it's increasing pattern. Especially the pre-monsoon month of March and April showed the most substantial increase during the near future. This is the monthly maximum stream flow change for the mid future. Here also you can see that the April month under SP5 8.5 scenarios during mid future showed the most substantial increase of about 70%. This is the per future multi-model ensemble box plot, and the percentage change is from the bar chart clearly shows that the pre-monsoon month of March, which showed about 90% increase during the SP5 8.5 increase. And all of them must show similarly increasing pattern. This is the N1 mean flow at Bhadra outlet for near future. This is the mid future N1 mean flow, and this is the per future mean flow for all of the 13 GCMs. And if I summarize them through a spider plot, here you can see that the left plot basically indicates the SP2 4.5 percentage change from the baseline for all of the 13 GCMs. This is the SP5 8.5 is shown in the right spider plot. If we compare both plots, here you can clearly see that the spreading is much higher in the case of right, which is the SP5 8.5 centimeters. So, which indicates the growing range of uncertainty during SP5 8.5 series in all of the future periods compared to the SP2 4.5. And if I summarize through a multimodal ensemble technique, through an annual mean flow ensemble, here for all the 13 GCMs, here you can clearly see that all the future periods show the increasing trend compared to the baseline. Especially in the case of per future under SP5 8.5 scenario, the increasing is much higher which is about 30% from the baseline. And using a flat frequency analysis, I have used annual maximum stream flow, which are simulated from the hybrid CNN LSTM model. I have done 3 frequency distribution tests. One is the Gumbel, log normal, and the log Pearson type G. And I have selected the best frequency distribution through 2 tests. One is the chi-square test and one is the KS test. And based on the lower chi-square and lower KS test value, I have selected the Gumbel distribution as the best frequency distribution. And this is the flat frequency analysis of annual maximum stream flow from the Gumbel distribution. And with respect to the baseline period, you can clearly see that from the figure A, all of the future periods show that increasing trend for all of the return periods. If I show the 100-year return period percentage change compared to the baseline, under SP5 8.5 there is about 45 to 6% increase from the baseline period. And this is the growing range of uncertainty, increasing trend of uncertainty. From this plot, you can clearly see that as we move on to the far future, which is the top three basically indicates the SP2 4.5 flood frequency, and the bottom three figures basically indicates the SP5 8.5 scenarios flood frequency. As we move to the future, you can clearly see that the range of uncertainty increases, which are basically indicated by the shaded region, which shows a 2.5 to 97.5% range for all of the 13 regimes. So if I conclude that our deep learning model, it can learn complex rainfall runoff pattern directly from images because they do not record detailed physical data like dam and use. And they can also provide this data at a faster rate compared to our traditional hydrological model. And it can also provide accuracy and reliability at a similar level with our traditional hydrological model. Our deep learning model, it could achieve accuracy up to 92% during training period and up to 86% during the testing phase, which is on par with our traditional hydrological model, like Abdullah et al. Study and Alam et al. And if I summarize, conclude how the N1 info, in our case, we found an increasing trend in all of the future accuracy. Similar pattern also found from the Alam et al. Study. They also found up to 8% increase in the near future and 70% increase during the mid future and 25% increase during the far future. And the SSP-based study that have been conducted by Abdullah et al., they also found that the monthly maximum streamflow change will be much more substantial in the case of pre-monsoon month, especially in the case of March month, they found up to 75%, which is about 90% in our case. So the future projection show a consistent upward shift in streamflow for all of the return periods compared to the baseline, which indicates a likely increase in the intensity of extreme flow events under climate change. The shaded areas widen significantly in the far future, especially for SSP5, which highlights the growing uncertainty in projection with time, and it emphasizes the need for flexible and adaptive water management strategies. And my recommendation for further studies are, in order to increase the input variable, classes, as you will see, if a portion soil moisture, it can improve the accuracy of stream prediction, and also including the anthropogenic interventions such as reservoir operation and interbasin water transfers, it can also improve the prediction accuracy. Future studies, it could explore the hybrid frameworks that combine both physical-based hydrological models with deep learning models in order to enhance predictive accuracy. And these are the references I have used. Thank you.